In this video, we revisit the cyclotron and we put all of this content together on what we now know about electric fields and magnetic fields, and we'll talk in a little bit more detail about how the cyclotron works and particularly in part of its magnetic components.
The key concept for this lesson is that the magnetic field within the Ds of a cyclotron causes the charged particles to travel in a circular path so that they repeatedly pass through the electric field. And this is what was covered in the last lesson. We explained why it travels in a circular path, and now we're going to link it back to the cyclotron. So the expected outcome for today is to describe the direction of the magnetic field needed in order to deflect an ion in a circular path within the D of a cyclotron. You've also got another derivation, which is to derive the period of the rotation in the cyclotron. You've got a second derivation in this lesson, which is the kinetic energy of the particle when it leaves, given a certain radius of the cyclotron, and explain why the kinetic energy is independent of the potential difference across the Ds, and for some given ion depends only on the magnetic field and the radius of the cyclotron. And lastly, using the two equations that you've derived above to solve problems for given unknowns.
Previously, we looked at the cyclotron and its purpose and function from the perspective purely of the electric fields. We talked about creating potential, which then generates an electric field, and that accelerates a particle between the two Ds. Now we can actually analyze what happens inside these Ds and use the concepts of charged particles or ions moving in a magnetic field. We've seen that a charge passing through that potential difference will have a force, and if we direct that in the right way, which is why we have this alternating potential, it's constantly accelerated every time it jumps across the D, and this increases its kinetic energy. We've also looked at the uniform circular motion effect of a moving ion in a magnetic field in a previous lesson, and now we're going to tie that in with the cyclotron and use that concept so that the ion is accelerated between the Ds and its direction is changed within the Ds, and that puts the two pieces of electricity and magnetism together. Here in this picture we can see a bit of a representation of what is happening to the particle. So within the Ds the direction is changing, but its speed is not. So technically this should be speed and not velocity, because if direction changes then velocity is changing. But it has a constant speed. So it's changing direction, it's curving in this circle, but its speed is constant. When it passes between the Ds at all of these angled sections, it's accelerated by the electric field. So its speed is increasing and therefore its velocity is increasing. So we step this, we go from change of direction, increase speed, change of direction, increase speed. And we repeat this process every time that it does a loop. In this picture here, you're expected to be able to identify the region where the particle increases speed, where the direction of the particle changes, and where the velocity changes, as well as being able to explain where the particle accelerates. So have a go at this. See if you can pinpoint which of these points would match up with this description. Hopefully you said that the particle increases speed in between the Ds because that's where it's accelerated. The direction changes within the Ds, so as long as you label one or the other or both, that's fine, that's where it's churning. The velocity is actually changing at all 3 points because, as I mentioned in the last slide, it's changing direction in the Ds and it's accelerating within the Ds, and all of these correspond to a change in velocity, given that velocity is a vector. So if you change direction or magnitude, the vector changes. Where does it accelerate? Again, it's accelerating in all three technically because it's either speed or its magnitude is changing or its direction is changing. So if we're just talking about speed and direction, then we've got in the Ds and outside the Ds. If we're talking about velocity and acceleration, then that occurs in every aspect of this. This is just a context and will be covered further in a later chapter, but fluorine-18 is another radioisotope that's made in a cyclotron. In this case, fluorine-18 is made by colliding a proton with an oxygen-18 nuclei. The proton needs to be of a very high speed or a very high energy in order to overcome the repulsive force of the positively charged oxygen nucleus. So these two things don't want to come near each other. They're like charges, so they're going to repel. But we can override that by giving it a huge amount of energy so that it comes in fast enough that it overcomes that and smashes into the nucleus. When we do this, this ejects a neutron from the nucleus and we end up with our radioactive fluorine-18 that we want. So my picture here is a bit of an example of that. If you've seen this video from the NFL recruiting, you'll get it. Otherwise, it's a bit of a physics analogy to it. So the positive ion is coming in originally, and it's very slow. It's blocked by this electrostatic repulsion of the Helios nucleus because this is positive and this is positive. However, if we move it fast enough or give it enough energy, it can basically punch through this wall of electrostatic repulsion, hit the nucleus, and it punches out this ejected neutron. So that's what's happening within the cyclotron. The notation for this reaction would look like this, where I've got my positive ion, my charge, smashes into this oxygen 18, that produces the fluorine 18 that we want, and it ejects the neutron here. So we use fluorine 18 for bone and PET scans to monitor organ function and detect cancer. Some of these may have been covered last year, and later on in the year we'll talk a little bit more about some of these types of scanning mechanisms. Fluorine 18 decays by emitting positrons, so it's a beta plus decay, and when the positrons collide with nearby electrons, they annihilate and produce two gamma rays that travel in opposite directions to conserve momentum. So again, this ties in with the conservation of momentum that we talked about. If initially they had no momentum, then they have to have no momentum once they split, so they split in opposite directions, so their momentums cancel out. A PET scanner has a ring of photon detectors and uses a computer to create a three-dimensional image of the organ being examined by detecting the two-directional particles, these gamma rays that are ejected. And it puts all of these together as the fluorine 18 decays, and it generates this image of sort of different colors and resolutions of what we're looking at for an organ. A medical production facility located in Lucas Heights, New South Wales is the twin PetNet cyclotrons. These are small cyclotrons used exclusively to produce the fluorine 18, but the half-life of fluorine 18 is 110 minutes. So this only allows sites within about 2 hours max of the cyclotron to be able to provide PET scans. So ordinarily we would have to send people up to New South Wales to have this scan because it's just not possible to get it down here and use it in time. However, before the Royal Adelaide, or the new Royal Adelaide Hospital was built, we used to source fluorine 18 from Melbourne every single day. We needed time to prepare the isotope, send it to the airport, fly it directly to Adelaide, and then transport it to hospital. So this is a huge amount of resources, time, money, etc., just to be able to do this. However, the new SAMRI facility, the South Australian Health and Medical Research Institute, that was built next door to the Royal Adelaide Hospital in Adelaide, now has its own in-house facilities. So we now have a cyclotron and a radiopharmacy on site, which reduces the costs of this stuff and increases the number of scans that we can actually do on a daily basis, given that we make it in the same building that we test it. This is a great segue and a great example of a science as a human endeavour topic. So this was a snippet from the Sunday Mail about the cyclotron, and they're talking about the benefits of it and things like that. There's some interesting things about limitations, such as that's a $4 million machine. It's got 2.5 meter thick walls and it's buried 20 meters underground. So it's a really interesting topic to talk about that. It talks about how it's done, the application, such as 23 people have been injected with radio tracers, ideal for personalized care, etc. So it's a really good application of physics and how it's changing society. Going back to the components of the cyclotron, we've got our two big electromagnets at the top. We've got our ion source right in the middle. Remember, this is where it's ejected into the center of the cyclotron. We've got the circular path that's traced by the ions, which is not a component, but it's a representation of what happens. We've got the target out here, which is the thing we're trying to hit with a high energy ion. And this is the emerging beam of those high energy ions that's ejected. In between the Ds, we have our alternating potential difference. And we talked about why we can alternate it at a constant frequency and how we do that. In terms of the cyclotron's operation, given that we've got these two large electromagnets placed around the Ds, we're going to have a uniform magnetic field, as we've talked about previously. Between the Ds, the electric field is doing work on the ion to provide kinetic energy. It's accelerating it. Using those formulas, we know that work is Q delta V and kinetic energy is half mv squared, so we can equate the two together. The work done is equal to or is converted into that kinetic energy. The uniform magnetic field causes the moving ion to curve, and it travels in a uniform circular motion, which we also talked about in the last video. The potential is reversed by the time the ion reaches the D again, and this ensures that the ion is always boosted. It's never traveling opposite to the direction of the electric field, so that it's constantly accelerated. As the ion enters the next D, it has a slightly higher velocity, and using the formula that we've derived, the radius is equal to mv over qb, we can tell that if we increase the velocity, the radius will also increase. Therefore, the radius of the path will be larger every single turn, and as a result of this, we get our spiral outward path as it travels. If we repeat this process, increasing the energy and the speed of the particle every single turn, its radius increases, therefore it creates an outward spiral. We can say that the total kinetic energy gained is n, which is our number of turns, times the q delta v. So if kinetic energy was the work done on it, the work done is q delta v, multiplied by how many times that work is being done, and it's done every single turn. So kinetic energy in total is equal to n q delta v inside a cyclotron. If we're talking about the period for circular motion, it's given by 2 pi r over v. That's what we've talked about previously in UCN. It's the distance traveled divided by the speed that you're traveling at. This comes from the original time is equal to distance over velocity formula. It's the same concept, but we're traveling a circle, so distance is 2 pi r, the circumference, and velocity is just still plain old velocity. But from before, we know that the radius of the path is given by the mv over qb. That's the radius of the path within a magnetic field. So if we just combine these together, we've got a radius here at the bottom in terms of a magnetic field, and we've got a radius here that's related to a period of motion. We mash them all together, cancel a few things out, do some rearranging. We end up with this formula that T is the 2 pi m over qb. So we've derived this formula. The period of motion for the ion in a cyclotron is given by T for period is equal to 2 pi times the mass of the object divided by the charge of the object and the strength of the magnetic field. It's important to note, what are we missing here? There is something in this formula, or something not in this formula, that probably breaks a lot of common misconceptions. The period does not depend on the speed of the ions. Given that the period of all the ions on the cyclotron is the same, and they all reach the gap between the Ds, or the uniform electric field we could say at the same time, then we could actually say that it's easier to predict what frequency we need to alternate that potential. It's not actually changing. We don't need a changing potential that is increasing the rate that it changes as the particle goes. It's actually a constant time. This is because the ions closer to the center have a smaller radius and they travel a smaller distance at a slower speed. However, ions on the outside have a larger radius and they travel further, but they're traveling at a greater speed. Given that time is distance over velocity, all of the ions are going to reach this electric field at exactly the same time because the distance is cancelled out, so to speak, by the greater speed. So the potential difference can be reversed on a regular basis so that the charges continue to move through the cyclotron in one direction. And we can actually calculate what that is using this formula. An important statement to note is that the period of the ion, or the orbit of the ion, is constant, as when it is moving faster, it also has to travel further. So these two cancel out, so to speak. Therefore, a cyclotron only needs a constant defined frequency to switch the potential in the field, rather than an ever-changing pulse. This is not part of the course, but a bit of a reference side note. Given that we know these quantities, we can calculate the fixed rate at which the potential must be alternating. The frequency formula, which is F equals 1 over the period, gives us that Q times the magnetic field strength divided by 2 pi m is how often we need to change it. So all we need to know is the mass of the particle and the charge of the ion that we put in it, and if we know the magnetic field strength, we can calculate how often we need to alternate this potential. So you could take any particle, say the positively charged proton that we talked about earlier, you know its mass, you know its charge. If you knew the magnetic field strength of a cyclotron, you could calculate for yourself what frequency that potential difference is alternating. The next part is deriving the kinetic energy of the ions. So if we start with what we want, which is the kinetic energy formula, that's our half mv squared. We also know that the radius is mv over qb from before. And we can rearrange that for velocity. So the velocity of the particle is the radius times the charge times the magnetic field strength divided by the mass. We go back to our kinetic energy. But now we've got a new way of representing the velocity. So we plug that in and we get our v squared term, where v is now this symbol or this representation. We rearrange it all, tidy it all up a bit, and we get our formula for kinetic energy. So the kinetic energy of the particle is the radius squared times the charge squared times the magnetic field strength squared divided by 2 times its mass. That is another derivation that you need to be able to explain and show. The kinetic energy is independent of the potential difference. Whilst the larger potential will accelerate the particle much faster, it would then travel in a wider, larger circular path as a result of this. This larger path means it reaches the outer edge of the cyclotron faster, which in turn means it's done less turns. Less turns directly reduces the kinetic energy, given that the formula is nq delta v, where n is the number of turns. The increase in speed or energy by the field is therefore virtually cancelled out by the decrease in turns and the longer distance that it travels. So the kinetic energy is not affected by the potential difference. The kinetic energy of the emerging ions depends only on the magnetic field and the radius of the final circular path, such as the radius of the cyclotron itself. So the only way we can increase that kinetic energy is increase the strength of the magnetic field to make it turn more, and increase the overall radius of the cyclotron, such as having a bigger cyclotron itself. So there are 2 limitations: how big we can make the magnetic field and how physically big we can make the cyclotron itself and where we put it. Practice question for you. One of the earliest cyclotrons constructed had a diameter of 12.5 centimeters. The magnetic field strength was 3.00 Tesla, and it was used to accelerate protons. So calculate the period and its kinetic energy using the formula that we've just talked about.
You spin me right round, baby, right round, like a record, baby, right round, round, round. You spin me right round, baby, right round, like a record, baby, right round, round, round.
Okay, so using our formula for period, the 2 pi m over qb, we get 2.19 times 10 to the negative 8 seconds. And our kinetic energy formula from the previous slide gives us the 2.69 times 10 to the minus 13 joules. And it also said to give mega electron volts, so we convert the factor, we get 1.68 mega electron volts. Remember, electron volts is our 1.602 times 10 to the minus 19. We convert that, we get our mega electron volts from joules.
Workbook questions for this section are question 181 and 182 in the SASTA workbook, and I'll see you next lesson.